This is Jim. Jim enjoys chemistry, bad jokes, and looking through photos of him and his girlfriend Polly. The latter is his favourite bedtime activity. Jim, your phone. Well done, Jim. Hey, chin up, buddy. I might have an idea for you, and it comes in the form of SMPs. Not that type of SMP, Jim. Shape memory polymers, or SMPs, are a class of polymers that can be deformed into another shape and hold that shape. Then a stimulus is applied that makes them return to what they looked like originally. Light, IR, water, electric fields, but most commonly heat. The way the majority of SMPs work is down to their semi-crystalline structures. They can have ordered or crystalline regions and disordered or amorphous regions present at the same time at a given temperature. Depending on their chemical structures, they can be hard or soft regions. At the first glass transition temperature, there's two glass transition temperatures. I'll come back to that one, Jim. Anyway, at the first TG, the soft regions elongate while the hard regions provide some backbone, and the new shape is retained due to reversible net points. These could be physical interactions like hydrogen bonding, or they could be covalent bonds. For the purposes of this investigation, when I say glass transition temperature, it's this definition I'm using. The second TG is where the temperature is high enough for the chains to become mobile, and you ought to know what that means, Jim. Yep, that causes the reversible net points to be, reversed, and we see a return to the original shape. Pretty cool. I forgot about that. Anyway, that's what SMPs are. Let's put Jim out of his misery and look at what some of them can do. Not a problem, bud. In 2017, researchers at the University of California discovered an SMP that uses ion-dipole interactions as reversible net points to heal itself. Introducing polyvinylidene fluoride cohexafluoropropylene, or PVDF-HFP. PVDF-HFP actually exhibits self-repairing properties, and these properties are actually quite impressive. The research team have run tests on PVDF-HFP and found that amazingly it can restore itself to 100% of its original strength. But it will take you a full 24 hours of compressing it to reach that point. Furthermore, when PVDF-HFP is paired with a mobile ionic salt, the glass transition temperature becomes dependent on ion-dipole interactions, and compared to hydrogen bonding, ion-dipole interactions aren't very strong. In fact, the TG for PVDF-HFP is minus 62 degrees C. Well, you could. Your best bet is adding polyethylene glycol, but that would give you a melting point range that includes your body temperature, so unless you'd like your phone screen melting in your hands, it's probably best avoided. But fear not, for a team in Japan might have stumbled across a solution. In 2017, University of Tokyo graduate student Yu Yanagisawa was investigating adhesives when he came across a set of SMPs called polyether thioureas. The hard thiourea units in these polymers provide the chains with structure and robustness, but they don't lose the self-healing effects. In other words, they can repair themselves while still feeling like glass. The thiourea units can also make 2 hydrogen bonds per atom of sulfur, which promotes faster repair. Isn't that neat? A team of researchers found that a specific polyether thiourea was a particularly good contender for phone screens, TUEG3. The key thing about polyether thioureas is that there are different types depending on how many R groups surround the ether groups in a repeat unit. TUEG0 doesn't exist because you just form a water molecule, and TUEG1 doesn't exist because that would just be a primary alcohol. The research group did, however, study TUEG2, 3, and 4, as well as some reference polymers. On that note, no points for guessing TUEG3. Anyway, TUEG3 is formed from alternating thiourea and triethylene glycol units, but differential scanning calorimetry has shown it's amorphous, which, if you remember the start of the video, doesn't exactly line up with most SMPs being semi-crystalline. But the fact that TUEG3 is amorphous is actually very useful. Glad you asked. The thiourea units in TUEG3 actually make it a zigzag-shaped chain. This stops crystallization from being induced, but you still get a cis-trans and a trans-trans hydrogen bond from just one thiourea unit. It's extra hydrogen bonding, extra strength, and extra glassiness, but you don't need to heat TUEG3 to 120 degrees C like other hard polymers. Believe it or not, the glass transition temperature for TUEG3 actually lies around 27 degrees C. Much better than the minus 62 we saw earlier. And it gets better. TUEG3 is semi-transparent, which makes it ideal for shining light through for a phone display. And it only takes 30 seconds for a 2x2 cm square to repair itself. What's more, recovery back to 100% strength takes a quarter of the time as PVDF HFP does. TUEG3 needs just 6 hours of compression. Yeah, but that's good. And if you want, you can just put a small weight on the brake while you're sleeping. It can hold up to 300 grams in weight. Look, Jim, I don't know what else you want me to do. I'm trying to help you out here. Fine. Telechylic polymers, or oligomers, are polymers with reactive functional groups at the ends of polymer chains. Importantly, these groups don't come from the original monomers, but instead they've been introduced to the chains for further reactions. Yes, Jim, I'm getting to it. The issue is that their dissociation kinetics need to be fast for self-healing, i.e. the dissociation constant Kd needs to be greater than 10 seconds to the -1, and this gives rise to rubbery properties. Obviously not ideal as a replacement for glass in phone screens. Enter cucurbit 8 uril, or CB8. CB8 is capable of acting as a host for different guest groups, in particular perfluorophenyl and substituted phenyl groups. These backbones, known as 5FB8 and RB8, can accept secondary guest groups that influence Kd and can even get it to be lower than 1 second to the -1. Guess what that means? Wow! Exactly. And if you decrease the temperature from 80 degrees C to 0 degrees C, something interesting happens. If you have a CB8 host with a low Kd at 20 degrees C, it behaves similarly to higher Kd at more elevated temperatures. This means you can control the viscosity, so you can theoretically control the glass transition temperature. If we could tune it to be near human body temperature, that would be ideal. Right, I think we've got enough options here. The question is, which one's the best? Based on current research, I'd say TUEG3. Look, Jim, I know you like CB8. Even that involves releasing water, which isn't going to be great if it gets into the electrical components of your phone. TUEG3, meanwhile, seems to have everything we're looking for. Of the options we've looked at, it's clear that it's the best suited for the job. It's important to note, though, that self-repairing tech is still a very new field. It's impossible to say with certainty if TUEG3 will become the industry standard, if CB8 might prevail, or if something completely new will be discovered. So for now, your best bet is probably just spending the money on getting your screen fixed. Sorry, Jim.